Yeah, this is just for the demo. So this is not like the introductory session. Uh, I'm going to discuss some points which might be a little advanced. Not very advanced, but the approach is advanced. Okay. So look at this problem. When you look at the problem, what happens in an interview, right? That's what I wanted to kind of, bring up here. Suppose you're just told that, okay, you are given an array of integers, an array of numbers containing n distinct numbers. Numbers are essential integers, and they are in the range of 0 to n, right? Return the only number in the range that is missing from the array. So what is the only number in the range? So if you understood the question, that is something you can infer, because there are n distinct numbers there. Numbers means integers here. There are n distinct integers, and these integers come from the range of 0 to n. 0 to n has actually n plus 1 distinct numbers, the range, but the array has only n of them. So one of them is missing. So we need to find that missing number. Looks like a simple problem, right? But how do you approach solving this one? So if you are kind of if you solve many problems, you directly jump to some well-known concept already. But what typically people do is when they hear a problem in like in a LeetCode or in an interview or whatever, most people try to think of, is it familiar to one of the problems I have solved? Is it is it one of the problems I have solved, or at least very similar to one of the problems I have solved? Then I can just use it, right? That is how actually our human kind of brain works, right? So we try to see if it is already familiar. I'm going to just quickly solve it and kind of impress that I know this stuff. But that has two flaws. One is, first of all, when you're searching that way, there'll be a wide kind of space you search. Maybe you do it very fast there. But if you miss that, that means if your mind says, no, this doesn't look any familiar, it's not familiar to me, this problem, then there is a good chance that you go blank or you get into panic, right? So what happens is when you do that, you don't know what to do now. You are kind of stuck because this is not familiar to you. You don't know how to approach, right? That's when actually, yeah, we just generally say take a step back and then solve it from scratch. So instead, that is what we call it as systematic approach, right? So instead of you getting into that mode of panic, why don't you just start with systematic approach? Why? Because even if you knew the answer to this and then give the answer quickly in a couple of minutes, you think that you're going to impress the interviewer. But interviewer is not, as I told you earlier, most of these coding interviews are not about whether you know the answer to this problem. It is about, can you solve this problem on this part? So if you give the answer in 2 minutes, it is most likely you knew the answer. So you think you impress them, but they think you already knew it. So this question is not going to kind of help me in assessing whether this candidate is good. Let me ask another question and then assess based on that. So they kind of didn't even consider this your solution to some extent. Maybe they gave some credit, but you don't get all the credits like the way you think, right? That's why that is one bad thing, first of all. Another one is, if you don't get an answer, you kind of go blank. That's a state where you don't want to be. It's not an engineering trait. What is an engineering trait is, the trait of an engineer is, you see a problem, you approach the solve problem, systematically, depending on at what level the problem is, right? So that systematic approach is what you need to kind of show. If you're thinking you're going to impress the interviewer by giving an answer in 2 minutes, that is not going to impress the interviewer normally. What is going to impress is, if you show in the first 2 minutes, if you show you are a systematic problem solver, then that is going to impress. It's not that you have an answer there, but you have a proper approach. That's what they like, right? That is what is needed in an engineer, right? So how do we do that systematically here, right? I'm just trying to talk a lot more about this problem, even though this you should not be getting into that much of discussion now. But I'm trying to make these points. So what is the systematic approach here, right? And as I told you, in the phase 1 of learning, you should get the hang of programming, right? So where I also mentioned a point, for that, you don't have to know the data structures and algorithms well. Well, in the sense, say in this problem, they have already given you an array. So you need to know what is an array, right? That is needed. But it is not like you're using a new array to solve the problem, right? That is what is the knowledge. Suppose if you use a hash table here, that using a hash table is the data structure knowledge. You don't need that kind of knowledge here, right? You just have to go with whatever is given and then apply, solve whatever they're asking. So that simulation is the word I use, right? Try to see whether you can simulate whatever they are saying. And typically we use this word called brute force for that. So brute force is, we call it as a technique, but technically it is just, uh, absence of any technique, right? It's not like it is random. It's not a random method. It is a systematic method, but that is the first one. And what do we? It's not like, an inefficient method is called brute force. Brute force solution is generally hidden in the problem definition, right? There are slight varieties of brute force, but yeah, one of them is simulation. I'll mention one more thing here. Look at here. When you see the problem, they're asking for, uh, in the range of 0 to n, there is a missing number in the array. Find that missing number. So one of them is a missing number, right? Which one? So if I ask this question in a brute force way, in an exhaustive way, is 0 the missing number? How do you know whether 0 is missing or not? If it is not there in the array nums, it is missing. If it is there, it is not missing. So if it is missing, you found the answer. If 0 is not missing, then you ask the question for 1. Is 1 missing? If that is also not missing, is 2 missing? So this is kind of, you're going over all possible solutions. What is a solution here? Solution is one of these 0 to n. So there are potentially n plus 1 possible solutions. One of them is actually the feasible solution. Everything else is like infeasible or invalid. Okay. So the idea here is, uh, the bigger idea here is for each of these numbers, so number from 0 to n, you ask this question, is this number the missing number? How do I ask that question here? So that you need to figure out, right? So in brute force idea is, you don't get to the details actually when you're thinking at an algorithmic level. If you have to implement it, you have to worry about it. At the implementation, at the idea level, the conceiving the brute force idea, this is the idea you're going to have. For each number from 0 to n, right, is num not present in uh, not present in nums array. If this question is, this is the question you're going to ask. If this is yes, then you're going to say return num, because num is not present in that one. It's a missing number. If not, you go for the next one. So you are, because of the way the input is given, you are bound to get an answer yes for one of these n plus 1 numbers. What if you only run from 0 to n minus 1? Then what if n is missing? If n is missing, all of these are going to say no, it is not. It's not true that it is not present. So it is present. All of them are present. Then I come out of the for loop and say return n. Because if none of them are missing, according to the problem definition, n is missing. So this is my brute force idea. And this kind of brute force is called exhaustive search, right? This is exhaustive search. What is exhaustive search is, you are searching exhaustively for the feasible solution. Among all, these are all potential solutions, right? So there are not just n, yeah, there are n plus 1. There are n plus 1 potential solutions. And for each of them, you see whether that is the answer you're looking for. And the kind of problem you're solving here is called decision problem. Once you get into this whole study, you will understand these terms. But yeah, it's not like these terms are so important. But if you know these terms, you will quickly get to how to approach solving a problem. If I tell you, if I tell you that, see, this is a decision problem, can you try and exhaustive search on this? Then getting this idea is going to be not difficult at all. Actually, it is going to be super easy, because I already gave you the clue of how to write this algorithm, right? Because you just have to go through every possible candidate of the solution. So there is another term we call it a solution space. So solution space has exactly n plus 1 solutions. In that, one of them is valid and rest of them are invalid. So you ask this question. Now, how do I implement this? So this question, whatever I am asking inside here, it's a subroutine for my brute force. Normally, where we get lost in while thinking of these things is, we think we need to kind of figure out how exactly that needs to be done. I don't want to code this. You don't want to code this actually normally. In an interview, you just have to say this out loud. maybe just figure out how much time does it take to answer this one. How do I answer this question of given a number, I want to see whether it is present or not in nums. It's an unsorted array. So maybe a simplest idea there is just, sequentially search, linearly search, and then find it. So that's going to take linear time. So now this is where you can even mention the time complexity and all. So this question can be answered in O of n time, which is generally linear time. And this is going to be called like n times. So that's why the overall time complexity is going to be O of n squared time. So we have a O of n squared time algorithm, which is brute force or exhaustive search. Normally, you don't have to code these things. You mention these and then see how you can improve from here. So just for getting that bigger picture, how we are going to improve from here, I'll code this quickly and then show how do we go to the next stage, right? It shouldn't take much time, and this is typically what I do in the actual training sessions also. I show this coding live because you should get the hang of it. You should code it, right? At least while learning. So we have this n. So I'm going to use variable n because we keep using n. N is essentially size of this array called nums. Now, the kind of question I was trying to ask is for each num is equal to 0 to lesser than n, right? So now I'm asking this question, is num the missing number? If none of these are missing, then the final answer is going to be num. Now, how do I answer the question I just have, right? Write it in comments typically. If you are kind of trying to understand everything, that question is num the missing number. So how do I know that? Normally, I'm going to put a flag here. So the flag says that it is kind of, so if this number is present, then I'm going to say, so right now I'm going to assume that it is missing, right? The number is missing. So missing is true right now, right? Now I'll go through the entire array. So entire array, I can use loop like this, 0 to I, or I can use a simple way of coding something like this. Okay, maybe I'll use the C style way of coding. So which is going to just write right through this one. In some languages, you find it's much easier to, use iterator way of traversing. So, but yeah, anything is fine, right? So this is easier for everyone to understand. That's why I'm just end up coding this. Now I'm going to ask this question. If num is equal to nums of I, right? Then it is not missing, it is present. So if I find this one, I'm going to say, okay, it's not missing. So missing is going to be false. So far we didn't find it, so it was true. Now I found it missing. I'm going to come out and then break here. Now when I come here, outside of the for loop, so whether I came out because of I found this number there, or I just came out because I didn't find it here. So I'm going to ask this question. If this is missing, then we found the answer already, right? So we're going to return this now. Otherwise, okay, finally, I'm going to return this n, not num. Okay, if none of them are missing, this is going to be missing. So now because of that, if you see here, this is going to take linear time, right? Normally I write like here, O of n time here. And this one, I can say just n times so that I know that there is O of n here. O of n times of n is going to be O of n squared. So that's why the overall solution is going to be like, O of n squared solution. Okay, n squared time. And if you talk about the space here, it doesn't take anything more than some constant extra space. I'm going to say O of 1 extra space, right? So these terms, big O notations, are vaguely used even in the interviews. You don't have to know them, very formally, with all the mathematical certainty. You just have to know in general, this we are talking about something called order of growth here. O kind of roughly means order of growth, right? It's also called an upper bound notation, but you don't have to get to there. O sounds like an order. So this algorithm takes an order of n squared time. So order of n squared time is, it could be like 2n squared or 4n squared or half of n squared. All of these are also just order of n squared. So in mathematics, we call them as, it's a quadratic polynomial. It's a polynomial that is quadratic. That means the highest degree of the polynomial is square. Okay, so this is going to work, right? How do I make sure? In an interview, you may not have that luxury. You may have to take an example and run through this one to illustrate, but that is not a proof of it is working. It is only a sanity check, right? But yeah, so at least in LeetCode or in any of these platforms where you can compile and run, you have this luxury, right? You can run against these test cases, right? And if at least these test cases work, sometimes the interviewer asks, like there might not be a way of submitting and making sure with the larger test cases. They may ask you, can you come up with all the border cases of your own and then test here? So you may have to look at what are the boundaries here. Typically, there is one boundary for the larger test case, but apart from that, are there any other border cases? What is the smallest size of n nums? Look at the constraint here. It says n is at least one. So you cannot have an empty array. If there is an empty array, so obviously you cannot have two here, because if n is one, only 0 to 1 are allowed. 2 is not even an valid thing. So it is going to say it's an invalid test case, right? So maybe having like a 0 or 1 is going to be the answer. If I have 0, maybe have one more test case where you're going to have 1. So that way, in this case, it will return from line number 17. In this case, it will return from here, line number 15. So that is something you can figure it out. Okay, so these test cases help you design that way. And here I can submit the code, but if it is an online platform, you can use one more thing. Look at what is the size of n, the worst case value of n, which is 10 to the 4 here, 10,000. And it takes O of n squared. So n squared, when n is 10 to the 4, n squared is going to be 10 to the 8. So 10 to the 8 is generally okay. In any online platform, roughly 10 to the 8 number corresponds to 1 second of execution. 1 second in time, absolute. So that's why anything that has less than 10 to the 8 as these operations in terms of complexity, generally these are acceptable, right? But if it is greater than 10 to the 9, you can be almost sure that it will cross the time limit. So they say time limit exceeded. This is like an error. It doesn't mean the solution is incorrect. It is only inefficient from their perspective. So anything in between 10 to the 8 and 10 to the 9 is like a gray area. Sometime it is going to be accepted, sometime not. In most cases, that is inefficient. So there might be a better solution. But here right now we got 10 to the 8. So we are still not into that gray area so much. So probably it is going to be accepted. May not be the most efficient solution, but it might be acceptable, right? You provide something like this. Okay, so see, it accepted and it took like more than 2000 milliseconds, more than 2 seconds. Yeah, sure. So this is expected. And look at 5 percentile, where I stand. What is this 5 percentile thing is, among all the C++ submissions for this problem, there are about 5% of the submissions that are slower than mine. 95% solutions are faster than mine. So most likely mine is not the efficient. If you look at the plot here, while practicing, you want to know whether there's a better solution or not. So if you look at here, I took like more than 2000 milliseconds, and look at the plot here. Majority of the solutions are like lesser than 100. They don't even have more than 75 milliseconds in the plot. So we are like clearly an outlier. So definitely my solution is going to be inefficient. There must be some better solution. Okay. Okay. Let's see. So now that we know it's an inefficient one. In LeetCode, in online platforms, we have that. But what happens in an interview if you give this solution, right? So you should not insist on, okay, I'm going to implement it, I got a solution, because you probably get the chance to implement only one solution in code. Rest of them you can only talk. So if you think there is a better solution, you kind of take a pause and maybe hint that probably I can come. This is just a brute force solution I have in my mind, but I think I can come up with a better solution, and then they're going to allow you. Or in the interviewer itself is going to ask you, sure, I think you got a correct solution. We are on to a good start. Can you now improve the solution? Can we make it better? Can we come up with an a more efficient solution? So in that case, try to improve here. So if you just not totally discard the solution and go elsewhere, you kind of not using whatever you started off with, right? This is not just like, I had to come up with the brute force. I came up with this now. I'll discard this. I'll now think of a more efficient solution. It's not exactly that. Sometimes you have to do that, but at least not here. Now see, how do you improve here? especially when you have an exhaustive search solution like this, for there are n possible candidates or solutions, n candidates. In that, you find like for each candidate, you spend linear time here. See whether you can get rid of this one at least and still use exhaustive search, but now you can answer this question faster. So how do you answer this question faster? So what is this trying to do? If you just look at here, you'll understand better, right? So there is a number called num. You are asking, is num one of them in the whole array called nums? Because it's an unsorted array, we take linear time. So now your knowledge of this data structures is going to come into play. Is there any other data structure where I can transform this array into that data structure where I can answer this question faster? Right? If you are experienced a little bit, you'll get that, oh, hash table is meant for that, because in hash table I can search for whether there is a number or there is an entry is there or not in constant time. For that, I need to kind of move all of these entries in the array to a hash table. I'm kind of transforming the array into a hash table thing. Hash table essentially is a set in mathematics, right? In set in mathematics is it has like distinct elements, and set is all about membership of elements there, whether it is there or not. Now that is the knowledge I'm using. I'm using some understanding from mathematics and some understanding from data structures, right? So if this solution is not good enough, I'm going to just comment it out. Now I'm on to a second solution where I'm going to ask this question in a little more. I'm going to answer this question in an easier way. So for this, I'm going to ask, is this num present in the set of nums? I'm going to use that word called set of nums instead of just nums. So I need to pre-process that. So that's why I'm going to have set. But a set in C++ language is just what is called unordered set with the data type here. So now this is like set of nums for me. So I need to have all of these nums, and in C++ things again are simple here. I'm going to provide this range of numbers from begin to end of the array. So this will take all of them and then add it into a set of nums. So this is like preparation already. And this line itself, you must be knowing that it takes O of n time and O of n space, also extra space, because this was not part of the input or output. All right. Now, how do I answer this question now? Is nums present in that? There is a direct way of that, right? So see whether set of nums contains this nums. Contains is find here. I'm going to find if num is present, right? So if this find returns something which is not like a null pointer, that means if it's, I need missing, right? Sorry. What is the question I'm asking? Is it not present in this one? So I need to know whether it is not present or not. So how do I know it is not present? It is going to return some kind of iterator, which is kind of a pointer in disguise. It's going to return something called end of set nums. End of set nums indicate we didn't find this number at all. So this indicates num is not present in the set of nums. If it is not present, we know what to do. We need to return num. That is the missing number. So this whole question, whatever we asked, works in constant time instead of linear time we used to take in for loop, right? Otherwise, things are again same, right? Okay, so this will just answer it. So now this is going to run, but if you look at the time complexity for analysis purpose, this one line already took O of n time. This for loop will also take O of n time because there is constant time operation here. N plus n is still O of n. So it's like linear plus linear. N plus n is 2n. 2n is still linear. That's why I'm going to say it's O of n time. And we took O of n extra space, right? So the technique we used here, if you want to kind of know about the technique names, the technique we used in the first method is brute force, is a little more vague term. But within brute force, I can even use a term called exhaustive search, right? That is the method I used here, exhaustive search. And what is the second method here? I'm still using exhaustive search actually. This for loop, outer for loop indicates it is an exhaustive search, right? But the thing is, along with the exhaustive search, I am already using another technique where I transform the input to something else by using some extra space so that I can answer these things faster. So there are a bunch of terms that are used for that. Exhaustive search is obviously an and outer logic we have, but inner logic is we used what is called transform and conquer, right? What is transform and conquer? We transformed the input into something else so that we are going to use that. Earlier set of nums was in the array form, but now they are in the hash table form, right? Vector is an array and unordered set is an hash table. So this kind of transforming the input to something else is going to be transform and conquer. It itself is a name to a technique. You don't have to really worry about these names so much unless they kind of help you in terms of thinking in some direction, right? So these names, these classifications are meant to guide you through solving a problem rather than they become a headache of, oh, I need to remember all of these things, right? So forget about the exams now. It is about, whether if it is useful or not. The purpose of these names is just using this term will give some kind of already a story behind it or a direction behind it, right? So transform and conquer. One more name people use is called space and time trade-off, right? It's not a very useful name as a technique, but what is the thing we are using here is, so we are spending some extra space here. We are trading off this extra space for an improved, time complexity, improved running time. So that is why it's called space and time trade-off. Space and time are kind of, are trading off here. If I become a little inefficient in space usage, I become efficient in time here. It's not always true, but whenever it is true, it is going to be that. But both of these kind of techniques are kind of pre-processing based. So this is not an official term people use. Yeah, so if you look at the textbooks and the algorithm experts, if you look at, so they don't use this word called pre-processing. These terms are used by some authors, but yeah, I like this kind of term because for me, if I think of, okay, can I pre-process the input and do it in a little more faster way? Yeah, I'll get this idea. Okay, so this is one idea. And now I already got a linear time solution. I can also prove that for this problem, you cannot come up with an algorithm that runs faster than linear time. You have to take at least linear time. You have to look at each number in the array at least once. Without that, you cannot decide, right? In the worst case, I'm talking about. That's why the time complexity wise, we already have the best possible thing. Okay, but space wise, probably we can get still better. Right now, when it comes to pre-processing, is there any other way of processing and then making it better? One of the other thing is, what if I convert the input array? It was unsorted. The reason why we took more time for searching here is it wasn't ordered in any way. What if I kind of pre-process so that I kind of sort this one, and then can we solve it in an easier way? So that is the next technique for me, right? If I sort it, then I may not have to kind of stick to this exhaustive search, right? Or I may want to or may not. Both are actually possible, right? Let us see if I pre-process where it is going to take is something I want to kind of explore. So we have solution 1 done, we have solution 2 done. So now I'm going to go to the next one. So these things are, I'm not just trying to show off, or this problem can be solved in so many different ways. What I'm trying to show here is how you can think, because not every idea is going to click in an interview. Whatever that clicks, can you take in that direction? Are you kind of trained enough to think in these directions quickly? That is what is trained is, right? When someone is trained enough to do some for a skill, it becomes a habit for them. It becomes like more like reflexes for them. They don't have to force themselves to think in that direction. They're going to do it, right? Because that's like muscle memory, right? That's what I want you to come to. That I have that in a way already now, but I'm trying to teach you guys or teach people how to get to this kind of skill part. It's not skill part. When you practice a lot, there is a tendency of remembering the solutions. I'm not really supporting that. That is not really a good way of learning. You should not remember that one. You should kind of it becomes like a habit so that you do it faster that way, right? So for example, I keep giving these analogies for skill because they are very relevant there. Suppose you're driving, car driving is a skill you're learning, right? And you're supposed to practice a lot to become good in driving before you come to the traffic, right? So if you're practicing on one particular road or one particular ground where there is no people and traffic, so you're practicing driving there. So people say you practice a lot. When you practice a lot, if you focus on that particular road, how that road is, and then you try to make it ride smoother because you know every pothole in that, every turn in that, so you become really good driving in that particular road. That's a mistake of practice. If you do more of that, you end up remembering those things. When you're driving on that road, like for the 100th time, you remember there is a speed breaker there, there is a pothole there is a turn there is a blind spot there. You already know all of those things, and that is generally okay. But for the driving skill, it is not really helpful. When you practice a lot, you become good at driving. If that is a new road, how are you going to drive it? So remembering that speed breaker there is not the skill we want, because when you go to the actual traffic, you don't know anything about that road. You have to make that decision. So that's why focus on the approach, how to drive. What are the things I need to do when I see a speed breaker? How do I put brake? How do I handle these things? Those are the skills, not remembering exactly where that is. So that could happen here also. If people say you practice a lot, I also say that. So, but if you solve this problem like 4 times, whatever the methods I showed you, you end up remembering these solutions, and that's a very bad thing, because now this example is useless because it's not really improving your skill. You're only remembering the solution. You're supposed to kind of get the idea of how to solve it. You're supposed to capture the whole method of solving it. All right. So let me quickly go through this one in the interest of time. I don't want to take a lot of time. I'm not going to explain everything now. I'll just quickly show. I'll think loud and then try to do that. Think loud is a way of communicating to the interviewer what you're thinking, because they want to know that, and it is better they know that. If they don't know, they don't appreciate your solution. If they know all the intricacies of your thought, then they appreciate even if you make some silly mistakes, right? So what is the next thing? I'm going to pre-process. So I don't know whether it is going to be exhaustive search or something, but I'll pre-process. So let me see what is this pre-processing for me. This time I'm going to sort it. I'm going to sort the array called nums. So instead of an unsorted array, what if I have a sorted array? See, the sorting itself is a cost here, but let us see whether is it going to be worth or not. Okay, this sorting. This itself is going to take off n log n time. Okay, that is costlier than n, but hold on to that. This is just a technique we are kind of exploring. Now, how do I ask this question now? Is this num present in num array or not? One simple way is, because now, if at all it is kind of present. So let's see, how do I do that? Okay, I can actually do it in a little more trickier way. So when I keep going in the array, so when I sort it, what happens if you observe? If there's a missing number, I'll take this example. There are actually 9 elements here, so in the range of 0 to 9. So one of them is missing. I think 8 is missing there. So when I sort it, the array is going to look like this with the indices I should write. So we have indices from 0 to 9. So 0 to 8, because there are 9 numbers. And look at the values. If I sort, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8 is not there, and it's going to be 9 here. Okay. So all of these numbers, if I just traverse through this array, index and the value are going to be identical here. And the moment index is one lesser than the value, that index is missing, because 8 was supposed to be here. 8 is not there. That is why we have 9. So that is how I can find it. So I don't need a quadratic time. I just need a linear time here, right? So I'm going to go through this array now. Maybe instead of calling it as num, it is num actually. So now how do I know num is there or not? So you see, you treat num as an index now, and you see at nums of this num, do we really have num or not? So, but at some point, if nums of num does not have num, right, it should be more than that. So if this is greater than just num, that's what happens, right? At index 8, index is 8 here, num is 8, but nums of num is going to be 9, so that is greater. So greater or unequal, both are same in this case. This is the place where I can say num is missing, right? So if none of these 0 to n minus 1 are missing, n should be missing. Now look at here, one condition is good enough here. So this also works in linear time here, right? So now this part worked in linear time, right? I can say this part takes linear time. But there is a pre-processing stage, which is going to take O of n log n time. So that's why now I can say this method takes O of n log n plus n. Normally, I don't have to write plus n because it is O of n log n itself. But does it take extra space? In the way I have done here, it actually doesn't take extra space because I didn't allocate any memory, right? The sort, I can assume that it doesn't take extra memory. But I modified the nums. So we call that as nums is mutable. Mutable as in it is modifiable. Immutable means it is not modifiable. If it was immutable, then I was supposed to take a copy and then make O of n extra space, right? So if it is immutable, then it is going to be like this: O of n extra space and nums is immutable. Depending on whether nums is mutable or immutable, that extra space is needed. Okay, but yeah, still it is exhaustive search in a way because I'm asking this question: is num missing or not? So pre-processing is still there. Transform and conquer is still there. And this is not actually space and time trade-off. There is a name for this technique. It is called pre-sorting. We sort it first and then we process it. It's also kind of pre-processing. Right. So these are the kind of things you can think in the beginning. What if I use some well-known thing? This is where your knowledge of data structures and some of these simple techniques are going to be helpful. Okay. But now once you have something like this, you kind of took more time, but in case of mutable, you actually saved space. So you can say that, see, it is better than solution one clearly because it takes only O of n log n time. But now it is better than solution two because it takes lesser space, but better than the solution one speed. So in a way, in one way, solution three is better than solution two. In the other way, it is not exactly. Right. So that's how I show the improvement. But now as an interviewer, I can ask you, can see we have sorted here and that is kind of dominating in the time complexity here. What if the input was sorted to you already? So it's given as sorted to you as an input. Then you don't have to do it and this whole thing is going to be O of n time. Can you solve this in a faster way? Faster than O of n, right? So that is where you can look at the structure of the sorted array and see whether you can actually solve it in a more efficient way, right? I'll show you that this is a technique where you might need. If you look at the way this array is, it is sorted clearly. Not every time sorted means binary search can be applicable, but binary search can be applicable here, right? How it can be applicable is that is actually a little bit of an advanced technique. So we are not going to use the basic binary search here. So we transform the array into some kind of predicate array and then we search for that. Essentially what happens is, I'll take maybe one other example slightly. What if instead of 8, say 5 is missing? In that case, we have this similar array here. 0, 1, 2, 3, 4. 5 is missing, so we're going to have 6, 7, 8, 9. So if you observe here, when 5 is missing, we have 6 here at this place, and all of these locations previous to that have index and number matching, and after that all of them are mismatching. Actually value is 1 more than the index. The same thing happens in any of these places, right? So it's like true for all of these things and false for all of these. If the question I ask is the value and index are not matching, right? And the first one is what we need to catch. So that is what actually binary search can do in a little more advanced or generalized technique. So if I use that, I can answer this question in log n time instead of linear time. So it is still binary. All of these are going to be applicable, but on top of it, it's like one more technique I am going to be applying. So along with pre-processing, pre-sorting, I'll also say that I'm going to use binary search. So when I use binary search, let's see what happens. This whole thing, I'm going to answer in a little more efficient way. So that is, I'll quickly write how binary search works here, but you don't have to know exactly. When you learn about a generalized binary search, you will understand better. So I'm searching in the range of 0 to n, and while low is lesser than high, I keep searching. In every iteration, I'm going to find the midpoint, like in typical binary search, right? High minus low by 2. This is the midpoint. And if that the question I'm asking is if mid is not equal to nums of mid. If this is true, then we are on the right side. In that case, I'm going to reduce high to mid. In the other case, I'm going to increase low to mid plus 1. That's how it is going to keep narrowing down. When low is equal to high, it's going to return. and that is the index we want. So I'm going to return low as the answer, right? So here, this whole thing took actually login time, O of login time. This took more time, but what if the input is already sorted? We actually just take login time. That's why the time complexity is going to be down to O of n log n plus log n. So if the input is sorted, this will go off and I have a O of log n method, right? So that's what I wanted to kind of show here. Okay. Okay, so it should work and it should accept now. Look at here. Yeah, because it's n log n, it is taking some time. Otherwise, it would have been negligible amount of time. And look at the improvement. I didn't submit the solution 2 and 3. They are also correct. But yeah, it was taking 2000 plus milliseconds for O of n squared time. But now it is taking very less time, like, less than 50 milliseconds. So we are already onto a very efficient method. But another interviewer, I can keep asking. I look at these numbers, not the runtime, absolute runtime here. They depend on the actual test cases we have. But this is more at an algorithmic design. So can we improve this one? Right? So far, we have these solutions at the moment. But now if I ask you, see, we are sorting it here. And if you look at the array, it's not a very generic array where we just have some n numbers of the whole number space, like 32-bit integers anywhere. And n could be very small, but still anywhere there, and we're going to sort it. But here it's a very specific kind of data. So knowing that, can you sort it faster? If that is the question I'm going to ask, because here the bottleneck is about sorting. Now, can you sort it faster knowing this one? Now that question is directed towards a particular technique. If you know that, actually you can answer it. Otherwise, again, you cannot answer it. Just like if you don't know this kind of binary search, you can apply it or you cannot apply it, right? See, knowing these techniques is essential to get to solve using this method. But the thing is, to come to even this point and realize that I can apply binary search is actually a bigger skill, right? And that is one kind of skill you need to have. And on top of it, if you don't know the techniques or the concepts, you come here, but you don't know there is a technique, and then you just go. It's like, you came to the door, but you didn't know that the whatever you're searching is inside that room, right? Because you don't know the concept. All right. So now the question I'm directing is, can you sort it in a faster than n log n time, knowing that we have a specific kind of data where there are there is a n distinct numbers in the range of 0 to n. So when you have like indices and numbers are kind of matching, there is one technique which is used in group theory called cyclic sort, right? That kind of concept we can use. So cyclic sort is something I can quickly copy paste and then show it to you, because it itself is going to take some time to show how it works. So what I'll do is I'll just make a copy of this whole thing and just use that method from elsewhere. Okay, so this is solution 4. We are done. Okay, now solution 5, I'm trying to use cyclic sort here. So I'll just remove everything else and then copy this cyclic sort solution. Okay, so let's see. Give me a second. Okay, let me just copy paste this. Look at here. This is going to take some time because it's a concept from group theory, and if you don't know cyclic sort, it will take time for you to digest it. I'll just quickly show it to you. I'm just leveraging the idea that the numbers and indices are kind of very much matching. So what I essentially do is, if you take this example, I'll just try to show what is going to happen eventually in this method. You can actually try to figure out what is the logic behind it. It's not like you have to kind of read it in a book and only then you understand. You can figure it out. I'll show you what is going to happen here. So in this array, we have this array. I'm going to write the indices first. We have these indices, and the array is going to look like here. So we have 9, 6, 4, 2, 3, 5, 7, 0, 1. So the cyclic sort concept is try to move each of these values to their respective places. That means in terms of the indices. One of them is missing, I know. It could be 9 because 9 itself is not an index here, or some other index and 9 is present. Those are the two possibilities. So eventually when I sort it, all the other numbers except 9 are going to go to their actual places. The index and value are going to match. and the one that is missing, in that place 9 is going to go. If that is also not missing, then 9 has to be missing. That is the idea. But how do I do that? I know the final state. It's all going to be the 0, 1, 2, 3, 4, 5, 6, 7, 9. This is how it's sorted, but 9 is in the place of missing number here. If instead of 9, if something else was, instead of 8, if something else was missing, 9 would have been in that place. So how do I do that? I kind of use a cyclic idea. The cyclic idea is I start from here. Okay, sure, 9 should go to its place. There is no place, so leave it there, right? And then you look at 1 here, and you see that this 6 should go to its place. So I'm going to go to 6 here, and there is a 7 there. 7 should go to its place. 7 there, and 7 that 0 should go to its place, and then this 9 is going to go. And because now we started off with 1, so 9 will come here, right? So this is one cycle where I fixed 0, 6, 7, but 1 was part of the cycle, and in this cycle 1 is not there. 9 is going to settle in that one. Now again, I'm going to start with one more cycle here with 2. So 4 is going to go to its place, and that 3 is going to go to its place, and this 2 is going to go to its place, and 2, 3, 4 are fixed. Now again, 3 is done, 4 is done, 5 is done, 6 is done, 7 is done, 8 is not yet done. 8, 1 will go to its place, and whatever is there, that 9 is going to come here. So now if you see, whatever I needed, it's done. And this whole process, you can prove that even though it looks like a nested loop here, it actually works in linear time. And that analysis is also an interesting one. How do we know that it works in linear time? We can discuss it when we get to there, right? So now what I have here is I have a solution where it works in linear time now, right? Even the sorting works in linear time. And after that, there is linear time thing here also. So this I can convert to log n actually, right? Just like the binary search earlier. So the second stage can be either n or this one, but yeah, I'm going to just convert everything to just n. It takes linear time now because of sorting. And this O of 1 is just like the earlier one. I'm not taking extra space, but I'm modifying nums. So nums is mutable, right? So now the whole technique is now kind of converting into something else, cyclic sort, right? Or cyclic permutation, right? So all of these terms are used. Now we got to something really good, right? Nums, but except nums is mutable, this is the best we can get. I told you O of n is the best time complexity we can get for this problem. Similarly, O of 1 is the best space complexity we can get for any problem. So this is the best thing we have. But the thing is, nums is mutable. If nums is not mutable, the extra space is not really what we kind of see it as best. It is actually O of n if nums is immutable, right? Now that next question is going to be, can you, what if nums is immutable? Even in that, can do it in O of 1 n time and O of 1 space, right? Here I'm not really hinting in what is that solution going to be, but as an interviewer, I'm just trying to say there is a way of doing it. Can you try that, right? Here, okay, if you don't know how to get to there, I might give a clue here. In the interview, what happens is they're not just going to say, can you solve it? If you say no, then they're going to leave, maybe give 0 marks for that, and then go to the next one. That's not going to happen. It's not an exam, right? It's not an examination in college. So there, what they do is they try to give hints, right? So we need to do this one. There is a way of doing it. Can you try it out? I'm going to give some hints, right? So that's where they try to give some kind of hints, right? They might say that, look at this, think mathematically, right? Think mathematically. See what is the sum of all the numbers, something like that. Is it somehow helping you? What is going to be the sum of all the numbers in the array? Then you realize that if I add all the numbers, it has one missing number in the range of 0 to n. So the sum of all the numbers from 0 to n, right? If I take 0 to n all the numbers, and if I add all the numbers from the array nums of 0 to nums of n minus 1, each of them, like if I take and then subtract this sum from here, they kind of cancel out. Each of them are going to cancel out. Only one number in the actual 0 to n sequence is not present in the array. That will not cancel out. So that will remain, right? In other words, if I find the sum of all the numbers from 0 to n and subtract the sum of all the numbers in the array, then I'm going to get whatever I wanted, right? So let me quickly show that. Again, in the interest of time, I'll try to kind of, copy paste the solutions here now. So let's see, the next solution is going to be the sum of all. So this is going to be the thought process. Normally we should go through all of this exercise on our own, but just to show everything I wanted to show before I kind of conclude the session, I'm going to show this. So what I'm trying to do here is, look at, in this case, I have n, and sum n is like, 0 to n sum, right? Sum of 0 to n. It's not about the array, and this is uh, sum of all nums, all in nums, right? In the nums array. So that's what I'm trying to do here. From for 0 to n minus 1, I'm adding nums of I to sum, and I'm adding I to sum of n. So I just have to add n after that. So I'm going to add it. Then when I subtract sum from sum n, I get the answer. Now this one, if you observe, it only took linear time, and it takes constant extra space, and it is not modifying the nums array. It is immutable. So we got what we wanted, right? It cannot, nothing can beat this now. There is one small flaw in this one. That one small flaw is this sum n, or even the whole, this sum also, it can get really big. That means the values I have here could be within the limit. Suppose if I use 32-bit integers, let me see whether it is acceptable first, right? I'm kind of just talking about this. It should be acceptable. It is acceptable. Let's look at the constraints why it is acceptable. Look at here. Each value nums of I is in the range of 0 to n. So look at n. N is only at the most 10 to the 4, 10,000. So even if I have n equal to 10 to the 4, what is the sum of 1 to 10 to the 4? The sum n. The sum n is going to be like quadratic term, which is about 10 to the 8 or lesser than that. 10 to the 8 can safely be stored in int data type. It is a 32-bit integer, because int data type can hold up to little more than 10 to the 9, 2 to the 31, right? So that's why this is safe and it's going to work. What if I have this number a little bigger, or what if the data type we are using, int, whatever the data type we are using, is not going to support that much? What if this data type can only hold up to 10 to the 5? Then even though the actual numbers are still within the array, which are all valid, but the sum is going to overflow. We have an overflow issue, right? So the sum can grow really big, and then it's going to be have a problem. The final answer is going to be within the limit because we cancel them out. So that looks like a little bit of a bug in this one. Only in some scenarios when the kind of values we have, the sum n is there a chance of it overflowing the data type we have? It is not really a mathematical problem. It is more of an algorithmic problem, right? Because in math, integer is just integer. We don't talk about in math like 32-bit integer. It is also a math concept, but yeah, it's more of an algorithmic limitation, because mathematically this is sound, right? Now, because we are kind of canceling them, the way you should think is, now if they ask you, see, there is a possibility of this code being a buggy code at some scenario, can we fix that now? Now, because it's kind of canceling it, I might think of one particular solution. The solution is, what if I don't want to find the sum n and then this sum and then subtract here at the end? What if during this iteration itself, I keep canceling out? Because I'll have a total value which I'm going to return. And whenever I need to add I, I'm going to add it, and I'm going to subtract nums of I, because that is going to be subtracted anyway here, right? So that's the idea I'm thinking of here. So that's going to lead to a solution like this. It may not really solve the entire, the overflow problem, but look at this scenario. What I'm trying to do here is I'm having just sum. Now this is not just sum of numbers in the array. Every time I come in this iteration, I'm adding I to that sum and then subtracting nums of I from that. So that way it is somewhere kind of canceling out, adding up and then subtracting. So the way it is going to grow in this previous solution, it might actually be much better, but it's not going to guarantee an overflow bug to be resolved, right? Because what if the first n by 2 numbers are all really small in the array, or the other way? Actually, the first n minus 1 numbers when I add. So it can go to negative, right? What if I have all the numbers, the huge numbers in the beginning of the array? So I go negative, I'll go to a huge negative value because positive values are very small. 1 to n by 2 are added, and n by 2 to n are going to be subtracted. So that can actually lead to an overflow situation on the negative side. So there is still a problem. Now, this idea can lead to some other way of canceling out the numbers. Here we are trying to cancel out, right? Another other way of canceling out. If you don't get that, you might get a clue of, can you use some kind of bitwise operation which can achieve this job instead of using the regular algebraic proof here, which this is algebra, right? Sum of n numbers subtracted with all the numbers in the array. Instead of using regular algebra, can you use some principle from Boolean algebra and can solve the same problem? In Boolean algebra, there is one operation which is kind of a magical operation. It's called XOR, exclusive OR, that does behave like addition sometimes and subtraction sometimes. And especially when you XOR two numbers, they kind of cancel out. That is where subtraction happens, right? So that's why the solution I'm kind of embarking here is, which many people know the solution for this problem, because maybe because they remember this, someone else solved it and they saw the solution. If you have solved this problem, you with this XOR solution on your own, you did a great job. But otherwise, you just, like most of the people, you just heard the solution from somewhere. But there is a possibility of you kind of stumbling onto this one if you come systematically. This is not a foolproof method, but this is the best shot at solving any problem. Right now, here XOR solution, I'm not going to get to the math behind it. So I'm going to XOR I and also nums of I. And if once we do XOR of the same value twice, they kind of cancel each other. That's why all the values in this case, like 0 to 9, so each of them are XORed here 0 to 9, and from nums of I, they're also XORed except the missing number, right? That's why the final result is going to be that remaining number. So this result, look at here, at any point of time, XOR all is going to have the same type of data type as int. It doesn't need even a single bit more than that. It's the same number of bits, right? That's why the overflow scenario is also not there, and it will work with the best possible thing now. 0 of O of n time, O of 1 extra space, immutable array, and the data types are also kind of within the same limit. We don't have that overflow issue. So this is the best solution for the problem. Because it is the best solution, many a times you kind of remember the solution to this problem. Because when you're preparing, if someone tells you, did you practice on bit manipulation algorithms or problems that needs bit manipulation? There are a bunch of them, 5-6 good examples, and you go through them, and this is one of them. And because you went through that by this technique already, there is already a clue here. And many a times, even if there is a clue, most people doesn't solve on their own. They look at someone else's code and then they understood. So they think understanding solutions of someone else is learning. That is actually going to spoil your learning, because now you don't know how to solve this problem. Because it's like a puzzle. If someone already gave you the answer to the puzzle or suspense of the movie, then you lost it, right? You lost that fun of solving it in a way. And in this case, it is not just the fun. You lost the opportunity to use this example as a learning experience. That learning experience is gone for you. That's why don't spoil your experience, at least with good examples. The good examples are meant for you to learn a skill there, right? And if you knew the solution, you kind of were spoiled because of using something like that. That's why don't practice problems on bit manipulations directly. Understand how XOR works, what are the limitations of that and all. And then when you're solving a problem, when you come to this, or if someone gives you that kind of clue as a hint, then if you can catch it, then you're good at solving it. Okay, so that is the skill I'm trying to explain here. That is the skill that will help you. It's not nothing is actually kind of foolproof here, but that is the best shot you have, right? And even if you fail in this kind of approach, you still impress the interviewer because you are systematic in approaching the problem, right? In many companies, even though a working solution is actually something a very strong requirement in an interview, uh, an approach is obviously more important than the actual solution in many companies, right? And especially the companies like Google, which are really the tier one companies. I worked in Google, as I told you earlier. That the process of interview is actually very well matured there in that way, because there the interviewer, when they ask questions and they get the answer, they write in detail what did they ask, what did they hear from the candidate, and what were they expecting, and what do they think about their response. Some interviewers are not really good there. They think that okay, the candidate did not get the answer, so I'm going to give a lesser rating, like no higher. But when they write in detail, the hiring committee can figure out, no, 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 this approach was good, just that the candidate did not come to a solution. So it is not a very strong hire, but it is not no hire also. It is somewhat better than that. So they're going to improve the rating. And that's how you might get a job. You might clear the interview for where in the interviews you may not really have solved the problems, and you may fail in the interview where you got the solution in 2 minutes, and then you thought, I rocked the interview because I got the solution very quickly. And they may not give all the credit to you there, right? Because they might write, even if the interviewer says, okay, I asked this question and the candidate just solved it in 2 minutes and we are done, and I am going to give strong hire for this interview. The interview, the hiring committee may actually think otherwise. They think, okay, there was no method of solving it. How did the candidate arrive at the solution? So one plausible explanation is the candidate already knew the answer to this problem, so they didn't solve it on the spot. It's not a problem solving skill, so they may give lesser rating for that, right? That's why sometimes the candidates are very surprised. I did really good, but I didn't get an offer. Or the interview, they said I failed in that. Or sometimes they say, I didn't really do so good, but I got an offer. I don't know how they kind of selected me. Maybe their bar is really low. Maybe you don't know the process exactly what they're looking for. That's why those good companies or good interviewers or good hiring committee, they look at these kind of things, and this is how it should be. But because it's a human involved process, people have their own way of doing it, and sometimes kind of there is a mistake on both sides. Like sometimes the candidates overfit in their preparation. They remember solutions to 500 problems, and in out of like 5 or 6 attempts, companies, they're going to obviously crack one of them because they are familiar with so many problems. But when they crack it, if they go to interviews like this, the one I mentioned, they may not crack in any of them, because in most of the cases, the interviewer or the hiring committee is going to catch you didn't really solve the problem, right? That's why show the skill of solving a problem, right? And think loud while solving the problem. That way they know that you are thinking straight. That's why don't leave them in dark. That has serious repercussions on you, because they they don't know that you're doing it in the right way, systematic way. That's why don't ask for, give me 5 minutes, I'm going to solve and give you the solution, right? That's a very bad thing to say. Instead of that, don't even be silent for more than 20 to 30 seconds. You should speak up something. This is what you're thinking, right? Just show the direction. Sometimes they're going to quickly help there itself. Oh, instead of that, can you think in this direction, right? Unconsciously they help you sometimes. So keep them engaged, keep them in your thought process. All right. So when I go through something like this, I generally make a notes of this one, all the solutions, and share it with you guys when we go through. So this kind of document is just that. And for some topics, if I have some presentation slides, normally I avoid that because it kind of becomes like a lecture, but some of them are important, so I kind of show it here. Right, so I share all of these things with the participants. Okay, yeah, I think I'm going to stop the demo here. If I have any more questions, we'll take it, and we should really end before 8:30 p.m. India time. All right, so if you have any questions, please let me know. You can even type the question in the chat box and make sure it is visible to everyone else. Okay, Harish Kumar is trying to say something to everyone. Many people say that one has to read other people's code to get better at coding, problem solving. Is this a myth? I'm not saying completely it's a myth, but when you are learning the skill of solving a problem, it's a spoiler. So avoid the spoiler, at least while you're learning the skill, right? So again, if you go to any other problem solving or any other skill based learning, if you have too much help in getting done, like you are driving there and someone is sitting next to you and then handling all the steering wheel when you are when there is a difficulty situation, you will never learn that scenario. So you have to kind of sit in the driving seat and then do that. And when you read someone else's code, you are sitting in the passenger seat and learning by looking at someone drive. It is not going to happen so well. You only learn few things there, like some concepts by looking at that. Oh, this is how the expert is parking parallelly, or this is how they kind of drive in a steep road, something like that. So, but once you learn that, you need to practice and then do it. So only the specialized kind of skills you may have to look at someone else's, right? If there is a problem that needs something like, maybe I'll just give some names which is not popular, like segment trees. You don't know, as in maybe you yourself coming up with segment trees as an idea on your own in the interview, let alone interview on your own. If I give you even like one whole day, you may not be able to come up with that idea. So you have to learn from somewhere else. All of these well-known techniques are just learnings of other people's, right? You learn from that, but learn the bigger picture. Don't learn by looking at one example. That's overfitting when you do that. Okay, so that's why this is not totally a myth, but this is going to be a spoiler in the context I'm talking about. Okay, I hope I answered your question, Harish.